Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 2 for our MCAT Physics and Math playlist, and this chapter is titled Work and Energy. In this chapter, we're going to cover the following objectives. Objective 1 will cover energy, where we're going to explore the concepts of kinetic and potential energy. We're also going to discuss total mechanical energy and the principle of conservation of mechanical energy. Then Objective 2 is going to focus on work and power. Here we're going to define force and displacement, and we're going to examine how work is calculated, especially in systems involving gases, where work is related to changes in pressure and volume. We're also going to cover the work-energy theorem and the concept of power. Then our third objective is going to cover mechanical advantage, focusing on simple machines, particularly pulleys, to understand how they amplify force and make tasks easier. With that introduction, let's go ahead and begin with Objective 1. Energy is the essence of our very existence as individuals and as a society. The food that we eat gives us the energy to live, work, and play, just as the oil consumed by manufacturing and transportation systems power our modern industrialized civilization. And while the concept of energy is quite familiar, energy itself is rather difficult to define precisely. In our lecture today, we're going to define energy as the capacity to do work or to produce heat. One of the most important characteristics of energy is that it is conserved. The law of conservation of energy states that energy can be converted from one form to another, but it can be neither created nor destroyed. That is, the energy of the universe is constant. Now, energy can be classified as either potential energy or kinetic energy. Potential energy is energy due to position, and there are various types of potential energy, and they include gravitational potential energy. This is energy stored by objects due to their position above Earth's surface. Then there's elastic potential energy. This is energy stored when objects are stretched or compressed. Nuclear potential energy, this is energy contained within the nucleus. And then chemical potential energy is energy stored in chemical bonds between atoms and molecules. On the other hand, we have kinetic energy. This is energy due to the motion of the object. Various types of kinetic energy include motion kinetic energy. This is the energy of an object in motion, and it's directly observable as mechanical movement. Sound energy is the energy carried by sound waves, which is a form of mechanical energy through a medium. Thermal energy, this is the collective energy of particles moving within a substance, contributing to its temperature. And electrical energy is energy carried by moving electric charges, often electrons, through a conductor. So now we've defined both potential and kinetic energy and looked at examples of both. Let's go ahead and just hyper-focus on kinetic energy for a little bit. Any object with mass that is moving has kinetic energy. And this energy can be quantified using this equation right here, which says kinetic energy is equal to 1/2 mv squared, where m is the mass of the object and v is its speed. Now, one of the key aspects to understand about kinetic energy is its relationship with speed. According to the equation, kinetic energy is directly proportional to the square of the object's speed. This means that if an object's speed doubles, its kinetic energy increases by a factor of 4, assuming the mass remains unchanged. This quadratic relationship highlights how even small changes in speed can result in significant changes in kinetic energy. Now, it's also crucial to remember that kinetic energy depends on speed, not velocity. Speed is the magnitude of velocity, which means that kinetic energy is concerned only with how fast an object is moving, regardless of the direction. Therefore, an object moving in any direction at the same speed will have the same kinetic energy. Finally, it's important to note that the unit of energy, including kinetic energy, is the joule. A joule is defined as the energy transferred when a force of 1 Newton is applied over a distance of 1 meter. So 1 joule is equal to 1 kilogram multiplied by meters squared divided by seconds squared. Understanding these fundamentals about kinetic energy is really going to help us grasp how energy is conserved and how it is transformed in various physical processes. Now, in addition to kinetic energy, we also want to spend some time talking about potential energy. Potential energy is the stored energy in an object due to its position, arrangement, or state. And there are two primary types of potential energy that we're going to discuss here today. And that's gravitational potential energy and elastic potential energy. Let's start with gravitational potential energy. This depends on the position of an object relative to a reference point. This is a chosen 0 point of potential energy. The gravitational potential energy of an object is given by this equation right here, which says that gravitational potential energy is equal to mgh, where m is the mass of an object, g is the acceleration due to gravity, and h is the height of an object above the chosen reference level. Now, this equation tells us that the higher an object is positioned relative to that reference point, that ground zero reference point, the more gravitational potential energy it possesses. So, for example, an object lifted above the ground is going to have gravitational potential energy due to its elevated position. Then we have elastic potential energy. This is energy that's stored in objects that can be stretched or compressed, such as springs or rubber bands. When a spring is either stretched or compressed from its equilibrium position, that's its relaxed state, it stores energy. The elastic potential energy is given by this equation right here, which says that elastic potential energy is equal to 1/2 kx squared. Here in this equation, K is the spring constant. This measures the stiffness of the spring, and X here is the displacement from the equilibrium position. This equation tells us that the energy stored in a spring depends on both the stiffness of the spring and the amount of stretch or compression. So the farther the spring is stretched or compressed, the more potential energy it stores. Now, with a clear understanding of both kinetic and potential energy, we can now begin to explore the concept of total mechanical energy. Total mechanical energy is defined as the sum of an object's potential energy and its kinetic energy. And this relationship is captured by this equation right here, E equals U plus K, where E represents the total mechanical energy, U represents the potential energy, and K represents the kinetic energy. Now, when we discuss energy changes in a system, it's important to understand that if the change in energy is negative, then the system loses energy. And if the change in energy is positive, then the system gains energy. Related to this is the concept of conservation of mechanical energy. The concept of conservation of mechanical energy is grounded in the first law of thermodynamics, which states that energy cannot be created or destroyed. It can only be transferred from one form to another. And this principle is really central to understanding how energy behaves in a closed system. In a closed system, where only conservative forces such as gravitational or elastic forces are at work, the total mechanical energy remains constant. This means that energy may transform between kinetic and potential forms, but the sum of these energies does not change. However, it's crucial to note that total mechanical energy refers only to the sum of kinetic and potential energies. It does not include other forms of energy like thermal energy that might arise from non-conservative forces like friction. This is why the total mechanical energy of a system isn't always constant in the real world. When non-conservative forces are present, they cause mechanical energy to be quote unquote lost from the system, typically converting it into other forms of energy such as heat. So it becomes crucial to understand then that this loss of mechanical energy doesn't violate the first law of thermodynamics. Rather, it highlights the importance of accounting for all forms of energy to see that in reality, the total energy of the system, including non-mechanical forms, remains constant. And the apparent loss of mechanical energy is simply the transformation of energy into forms that aren't included in the mechanical energy equation. To better understand the conservation of mechanical energy, let's understand the distinction between conservative forces and non-conservative forces. Conservative forces are forces that are path independent and do not dissipate energy. These forces, like gravity or spring forces, they have associated potential energies. The work done by a conservative force then depends only on the initial and final positions of an object and not on the path it takes. This characteristic ensures that energy is conserved within the system. So, for example, the work done by gravity on an object moving between 2 points is the same regardless of the path it's taken. So it can take a path like this, or it can take a path like this, and for conservative forces, it only depends on the initial and final positions. And that makes things like gravity a conservative force. Non-conservative forces, on the other hand, they cause a loss of mechanical energy from the system. Forces such as friction, air resistance, and drag, they all fall into this category. The work done by non-conservative forces depends on the path taken, and it often results in the transformation of mechanical energy into other forms such as thermal energy. When non-conservative forces act on a system, they dissipate mechanical energy, causing the total mechanical energy to decrease. Now, the next thing we want to do is explore how the conservation of mechanical energy applies in practice. When only conservative forces are acting on a system, the total mechanical energy remains constant. And this can be expressed mathematically with this equation right here. This equation tells us that any decrease in potential energy will be exactly offset by an increase in kinetic energy and vice versa. So for example, when an object falls, its potential energy decreases, but its kinetic energy increases by the same amount, keeping the total mechanical energy constant. However, when non-conservative forces are present, the total mechanical energy is not conserved. Instead, the work done by these forces results in energy being lost from the system, often converted into heat or other non-mechanical forms of energy. This situation is represented by the following equation. Here, this term is the work done by non-conservative forces, which equals the amount of mechanical energy lost from the system. Although the mechanical energy decreases, the total energy of the system remains constant when all forms of energy are considered. Now, by understanding these principles, we can begin to analyze how energy is conserved or transformed within a system, and also how different forces impact the total mechanical energy. With that, let's go ahead and tackle some practice problems together. This first example says a 15-kilogram block, initially at rest, slides down a frictionless incline and comes to the bottom with the speed of 7 meters per second, as shown below. What is the kinetic energy of the object at the top and at the bottom of the ramp? Now, to calculate kinetic energy, we're going to use our expression 1/2 mv squared, where m is mass and v is speed. Now, to calculate the kinetic energy of the block at the top of the ramp, we know the mass, it's given to us in the question stem, 15-kilogram block, and we know the speed. The block is initially at rest at the top of the ramp, so the speed is going to be 0 meters per second. Let's go ahead and plug these values in. 1/2 multiplied by 15 kilograms multiplied by 0 meters per second squared. This is going to be equal to 0 joules. So the kinetic energy of the block at rest at the top of the ramp is just going to be equal to 0 joules. What about the kinetic energy of the block at the bottom of the ramp? Now here again, we know the mass, it's 15 kilograms, and we also know the speed of the block. As the block comes to the bottom of the incline, it has a speed of 7 meters per second, and this is going to be squared. So what we have here is 1/2 multiplied by 15 kilograms multiplied by 49 meters squared per seconds squared. Now I'm going to approximate this to 50. So what we have here is 1/2 multiplied by 15 kilograms multiplied by approximately 50 meters squared per second squared. Now 1/2 multiplied by 50 is 25. So now we have 15 kilograms multiplied by 25 meters squared per second squared. 15 multiplied by 25 is going to be 375, and this is going to be kilograms multiplied by meters squared over seconds squared. So this is 375 joules. So the kinetic energy of the block at the bottom of the ramp is going to be 375 joules. And there we have it. We've solved this problem. Let's jump into our next example problem. This example reads, an 80-kilogram diver leaps from a 10-meter cliff into the sea, as shown below. Find the diver's potential energy at the top of the cliff and when the diver is 2 meters underwater, using the sea level as our reference point. Okay, so at the top of the cliff, when the diver's chilling up here, what we can say is that the potential energy is equal to mgh, where m is the mass of the diver, 80 kilograms. G is the acceleration due to gravity, which is equal to 9.8 meters per second squared, but we're going to approximate it to 10, so the math is easier without a calculator. And then h is the height above the reference point. So he's at the top of this cliff, 10 meters above sea level. So our height is going to be 10 meters. What we have here is 80 times 10 times 10, which is going to be approximately 8,000 joules. And we're going to have 8,000 joules because our units are kilogram multiplied by meter squared over second squared, and that's equal to 1 joule. So again, the potential energy of the diver at the top of the cliff is 8,000 joules. Now, what about when the diver is 2 meters underwater? Now, we're going to use the same expression to calculate potential energy, mgh. The mass of the diver is 80 kilograms. G is going to be 10 meters per second squared. And here, the height is going to be 2 meters underwater. So if our reference point, our 0 point, is sea level, and he's 2 meters below sea level, then we're going to say that the height is negative 2 meters to indicate that he is underwater. And so now what we have is 80 times 10 multiplied by negative 2. This is going to give us approximately negative 1,600 joules. So that's the potential energy of the diver 2 meters underwater. Wonderful. Let's tackle our last practice problem before we move into objective 2. This problem reads, a baseball of mass 0.25 kilograms is thrown in the air with an initial speed of 30 meters per second. But because of air resistance, the ball returns to the ground with a speed of 27 meters per second. Find the work done by resistance. Now, air resistance is a non-conservative force. So to solve this problem, the energy equation for a non-conservative system is needed. So we can write that the work done by the non-conservative forces is equal to the change in potential energy plus the change in kinetic energy. Now, in this case, the change in potential energy is actually equal to 0 because the initial and final heights are the same. So that means that the work done by the non-conservative forces is just equal to the change in kinetic energy. So this is kinetic energy final minus kinetic energy initial. And we can expand this as 1/2 mv final squared minus 1/2 mv initial squared. Now you notice both of these terms have this 1/2 m. So I'm going to rewrite this expression to make some of the math a little bit easier. I'm going to write 1/2 m, and then in parentheses, I'm going to write v final squared minus v initial squared. Now let's work with this term first, 1/2 m. M is given to us. The mass of the baseball is 0.25 kilograms. I'm going to rewrite this as 1/4 kilograms because that's going to make the multiplication with 1/2 really easy. 1/2 multiplied by 1/4 is just equal to 1/8. Now the second thing we want to work through is this next term, this v final squared minus our v initial squared. Now v final is 27 meters per second. That's going to be squared. And then v initial is going to be 30 meters per second squared. And this is all multiplied by 1/8. Now let's focus on this 30 meters per second squared. This is easy. 30 times 30 is equal to 900. 3 times 3 is 9. And then we add in those 2 zeros. That's how we got 900. And remember that you also want to square your units. So don't forget that. This is going to be meters squared per second squared. What about 27 squared? I'm actually going to round this to 25 squared, and then I'm going to show you a trick of how to do this really fast. This is how you do the square of any number that ends in 5 and is less than 100. So for 25 squared, the first thing we do is we do 5 squared. That's equal to 25. These are our ending digits. Then we do 2 multiplied by 2 plus 1. So essentially we're going to do 2 times 3, which is equal to 6. So 25 squared is equal to 625. Let me demonstrate with one more example. Let's do 35 squared. First we do 25 squared. 5 squared, that's 25. That's our ending digits. And then we do 3 times 3 plus 1. So we have 3 times 4, which is equal to 12. So 35 squared is 1,225. Okay, that was a side note and just a little example to make sure you understand how to do this trick. And let's go back to our calculations now. So we have 625 meters squared per second squared minus 900 meters squared per second squared. This is going to give us negative 275 meters squared per second squared. Now, we can't forget that this is multiplied by 1/8, 1/8 kilograms. Now, the other approximation I want to make here is I want to approximate this negative 275 to a number that's divisible by 8 so our calculation is easier. I'm going to round this to 240 because 240 divided by 8 is equal to 30. 30 kilograms times meters squared over seconds squared. So this is equal to 30 joules. All right, now one more thing. Don't forget to carry that negative sign. So this answer is indeed negative 30 joules, and the negative sign in the answer indicates that energy is being dissipated from the system. And with that, we've completed this practice problem. I'm going to stop the video here. In the next video, we're going to continue the rest of this chapter. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.